So what we can see here, instead of having a loop from 0 to n, we've just said this is a function, and we're only in the function we're only doing one operation, which is doing c equals I, c of I equals a minus b of I, and we define I here to be a thread ID, okay? And this is something which CUDA gives us. It says, give me a thread ID, thread ID X in this case, and then when we run this, as long as we run it on the right number of threads, then it will run multiple copies of this, enough copies to do all the operations that we did in the original loop. Okay? So in this particular example, we then, in our code, we have this function we defined, and then we have these special things, and all these brackets are needed. So running using multiple CUDA threads, you have this bracket syntax, and we say, how many blocks per grid am I going to run, and how many threads per block? Okay. So if we remember the picture I had before, where we've got this two-level hierarchy, we've got blocks in a grid, and then threads in a block. Okay. That code that I was just running there, which just is a single loop from 0 to n, what I was going to say is I want to run that, I only want to use one block, so I've only got one dimension of my vector to do, and then I want to assign 0 to n threads to this block. So when we've run it, we've said number of blocks per grid is 1, number of threads per block is n, these are my data structures I've passed in, and that will run that loop for us on a single part of the GPU, and it will do the calculation once we will do the number of iterations we wanted. Of course, this isn't efficiently going to use a GPU because we have multiple blocks in that GPU we're not using one. We're only using one of them. But then there may be a different part of your program which could use the other blocks which are being used at the same time. Actually, most scientific programs, you're not doing a single dimension. You're not doing a loop over a vector. You're doing a loop over multi-dimensional data structure. So in practice, that one was fine, but actually we may want to go for multi-dimensional data structure. So we may want a 2D or 3D data structure. We may want to use multiple blocks and multiple grids. So we can define this. We can define these in different ways. So here we've still got a vector, single dimensional vector, but we're going to say our vector is going to be quite long here. So instead of n being the size of our loop being quite small, it's very big. So if we had a loop over 1 million elements in a vector, and we just stuck them all on one block on the GPU, that would be very efficient. But we can say, well, we can actually try and split up each part of that vector into different blocks on the GPU. And then we go. So we can do that by actually saying, well, the number we're going to choose 256 as to be the number of threads per block, and then choose as many blocks as you can split that up into. How many 256 you have in your full vector. Assign that out. It's still a one-dimensional object. Then we can index into that here and say this particular run is in from this block. Right, and this thread inside this block, so I'm going to calculate the actual element I'm going to. So this is just addressing calculations into the vector. And then this is going to be more efficient because, well, assuming that n is much bigger than 256, we're going to have lots of blocks to run on the GPU. We're going to have 256 threads per block. So we're actually putting quite a lot of work to do on the GPU. Of course, this code will completely fall down if n doesn't divide exactly by 256, right? Because something will go wrong there. We'll probably either do too much work or do too little work, and something will go wrong. But this is just an example. You would have to do something clever to deal with that in the real code. I mean, a lot of data structures are power of 2, and they're not all right. And this is actually really, so this is, maybe look like something strange we're doing for the GPU, but this is a kind of code modification that people have actually been doing for quite a long time to improve performance on cache architectures is, you know, something like strip mining or cache blocking of a loop. Right, so you say, well, I have this loop here which went from 0 to n over just these vectors. And what we've done on the GPU is actually split it up into two levels of the loop, where the internal loop is going from 0 to 256, and the external loop is looping over that. And that's not an uncommon thing to do to try and optimize cache performance on CPUs. It's quite common to see that, you know, because you know your cache is quite small and you want to work on the same bit of data at once, you can quite often see people lose exactly code. So it's not an optimization which is that new computer science. I should say that I can easily make these slides available. I don't know if will they go up online, Dana, afterwards, or as long as you put slides up? Yeah, I can give them to you. So. And of course, if you have multi-dimension data structures, you don't have to do this division yourself of a block, of a vector across blocks. CUDA lets you do 1, 2, or 3-dimensional data structures and fit them onto a grid. So as well as giving you a thread ID X, it gives you a thread ID Y and a thread ID Z, so you can define it using that. So CUDA has a DIM3 type, which contains X, Y, and Z components, and it lets you map your data structure directly to a grid and block structure on the GPU. Of course, if you have a data structure which is more than 3 dimensions, then you're going to have to handle this a little bit more cleverly yourself. But it gives you, you know. So this would be an example here where we have a 2-dimensional data structure, so we've got a 2-dimensional data structure. Inside here, we're iterating over a small block, and then we've got a grid of bigger blocks. I don't know how much this makes sense without actually doing it in practice. So that's sort of the fundamentals of how you split work up in CUDA. You create a little function, a kernel, and you tell it how to run it on the system. And you define how you split your work up inside that kernel using things that CUDA gives you, thread IDs and block IDs that CUDA gives you. So it's really designed, it's sort of really strongly designed around a data parallel idea of doing things. You've got all these big arrays, and you can do each element of them separately. So you see how you assign the elements of the array to the GPU cores, and it does the rest for you. Okay. But the other thing that you also need to do is copy your data to and from the GPU, because it's got its own separate memory. Okay, it's got its memory. It can't see the CPU memory. You only see its own memory to do its calculations, so you need to tell it. So CUDA gives you functionality to do this. So there's mallocs and frees and memory copy functionality, where you can say copy from this bit of memory to this bit, copy from the host memory to the device memory, copy from the device memory back to the host memory. Transfers between the host and device memory are slow, so that can be a bottleneck. So you don't want to be pushing data backwards and forwards if you can avoid it. You want to, at the beginning of your simulation, put all your data on the GPU, do all your work, and then pull it off at the end. It's the ideal model, because it costs you to move that data backwards and forwards. You can also have the concept of non-locking work in the GPU. So kernels can be non-locking, so you can run multiple different functions at once. So if you've only got a function using one block, you can run another function on another block,